to continue our discussion on two-dimensional projectiles. We've already done a lesson on what I've considered type 1 and type 2 two-dimensional projectiles, and now we're going to combine those two ideas into these, which I'll call type 3. So let's take a look at what a question like that looks like. A cannon is perched at a 48-meter high cliff. It aims 30 degrees above the horizontal and fires a shell at 52 meters per second. So now we've already dealt with projectiles that were shot horizontally from a given height, and we've dealt with projectiles that were launched at an angle, but usually from the ground or at some baseline that we consider the ground. Well, in this case, now we have a projectile being launched at an angle from a given height. And really all it is a combination of the two ideas we've already covered before. So if you haven't watched that video yet, I would stop now and go look at that first, okay? But for the rest of you, we always start with the same idea, and we start with a picture. So we have this pretty picture here, and what happens? Well, we know that this is 48 meters, and we know that it's going to shoot a projectile, and what's going to happen? It's going to fall and hit right here at some distance, dx, away from the cliff. Okay, so if we want to label the angle, we simply draw a horizontal line right across, so it's at the bottom of the cannon, and this angle right here, according to the question, is 30 degrees. So it looks like a type 2 type problem, however there's this additional height at the end that it has to fall, so it's got a different component than what you've seen before. But the first thing you should do, as always, is let's break this vector into components. So this is 52 meters per second. And we know because of perpendicular vector independence that there should be a Vx component and a Vy component. And we use trig for this, and we've already discovered some equations for this, so let's go ahead and use those. Vx is equal to 52 cosine of 30 degrees, which is equal to 45.03 meters per second. And we know that Vy is equal to 52 sine 30, which is equal to 26 meters per second. So now that we have all the components of the vector, we have to ask ourselves, what do we need to get the horizontal distance? And if you remember from the previous examples, the first thing we have to do is find the flight time, and from that we can use velocity equals distance over time to find the distance. So the first thing we need to realize is that to find the flight time we need the y component. So let's talk about the y direction motion. Well, we don't know what the final velocity is, but we know that the initial velocity is 26 meters per second. We know that the acceleration in the y is negative 9.8 meters per second squared. We also know that the distance traveled is going to be negative 48 meters. Why negative? Because we're moving down. We've established the cannon at the top of the hill as our base. And finally, we don't know what the time is. Now, there's two ways you can get time. One is a two-step method. The other is a rather straightforward method, but you have to have knowledge of the quadratic formula. So if you have knowledge of the quadratic formula, what you can use is you can actually use the quadratic equation. D equals VIT plus 1/2 AT squared. This is a quadratic, and if you take a look at the information we have this distance, we have the initial velocity, and we have the acceleration. If you plug those values in, it's not going to be a quadratic that you can factor. However, you can use the quadratic formula to get your solutions for time directly. I'm going to go through the two-step method, but it's certainly an idea that's worth exploring if you have the knowledge to deal with it, because it's certainly mathematically valid. For us, though, we're going to take a look at this idea that we don't have the final velocity. But if we do have the final velocity, we can use another one of the big three to get the time. So how do we get the final velocity? Well, we have initial, the acceleration, and the distance. So we're going to use Vf squared equals Vi squared plus 2AD. And if we solve for Vf, that's going to equal the square root of 26 squared plus 2 times negative 9.8 times negative 48. And if you've plugged it all in correctly, you should end up with a value of negative 40.21 meters per second. If you didn't end up with that value, I would check your negative signs underneath the radical there. chances are you dropped one more than likely on the 48 meters. So check, make sure, but this is definitely the solution you should get. So we have the final velocity now. So now we have the final velocity, the initial velocity, and the acceleration. We can use our second equation, Vf equals Vi plus At, to find our flight time. Solving for t equals Vf minus Vi over A. And if you plug in the values, negative 40.21, subtract 26, divided by negative 9.8, you should end up with a value of 6.8 seconds. Again, that's the sig figs, 6.756 for those that are carrying the digits. So there we go. We now have the time of flight. Well, why is this useful? Well, we can now find this distance because we know that it's independent. There's no acceleration in the horizontal direction, which means we can just use velocity equals dx over t. Dx equals vxt, which equals 45.03 times 6.8, which gives us a final distance of 304.2 meters. If you want to go to sig figs, by the way, that's equal to 3.0 times 10 to the 2 meters. So there we go. Again, it's a two-stepper to get the time, but then it's a very straightforward equation to get the distance. But 304.2 meters is the correct solution. So follow the steps. Again, it follows the steps of the other types of projectiles as well. Only difference, of course, is we had to find that final velocity first. Part B here, it's asking now for the total final velocity of the shell on impact. Well, you may recall that in part A, we found the final velocity in the y direction. However, we didn't find the total velocity or the resultant velocity adding up the two vectors both horizontally and vertically. So if we take a look, again, we always have the horizontal velocity vector, and in this case it was going at 45.03 meters per second. But now we found out that there is this second vector vertically that's traveling at 40.21 meters per second down. So that's why I've got the arrow down, which means our resultant velocity is this vector right here, going at some angle below horizontal. So the question now asks, well, how do we get that? Well, this comes back to the idea of trig and the Pythagorean theorem. So if we call this V total, we know that V total is equal to the square root of Vx squared plus Vy squared. Plugging in our values, 45.03 squared plus 40.21 squared, we're going to get a final total velocity of 60.37 meters per second. Now that we have the final velocity, we can find what angle below the horizontal it actually is. And for that, we'll use tangent. That's equal to 40.21 divided by 45.03. So theta is equal to tan to the minus 1 of 40.21 divided by 45.03. And that's going to give us a theta of 41.8 degrees. So therefore, the final total velocity is 60.37 meters per second, 41.8 degrees below horizontal. And that's our final solution. So let's take a look at a different example with similar ideas. A BMXer leaves a ramp traveling at 65 kilometers per hour at a trajectory of 40 degrees above horizontal. He strikes the top of a building 5.8 meters above the ground. What is the horizontal distance from the ramp to the building? Okay, well, again, we're going to draw a picture. And there's the biker going off the ramp. That is 40 degrees. And we're going to put a building a certain distance away. And this biker is going to fly and hit the top of that building. We know that this here is dx, And we know that this distance here is 5.8 meters to the top of the building. So when asked what the horizontal distance is, if you remember from all the previous examples, we need to find the flight time, and then we can find the horizontal distance traveled because of that flight time. But before we can do that, we need to find the components of the vector first. So we know that this is 65 kilometers, and we know that it has two components, Vx and Vy. Now, 65 kilometers an hour, not useful. Why? It's not an SI unit, so 65 kilometers per hour divided by 3.6 is going to give you an answer of 18.06 meters per second. Using that and the fact that this is 40 degrees, we can find our components. Vx is equal to 18.06 cosine 40, which is going to be equal to 13.83 meters per second. Vy is equal to 18.06 sine 40, which is equal to 11.61 meters per second. So we have our components, we have the strategy that we have to use, now it's just a matter of getting it done. I'm going to break this up into two ideas, y and x. In the y, we don't know what the final velocity is, but we do know that the initial velocity is 11.61. We know that the acceleration in the y is always equal to negative 9.8 meters per second squared. We know that the distance that we have to travel is 5.8 meters vertically. And the time of flight is something that we don't know. So, how are we going to find this? Well, again, if you choose, you could use the quadratic formula and deal with it that way. I'm going to break it down into the two-step question yet again. So the first thing I need to do is I need to find the final velocity that it's traveling when it gets to that point. And there's something I want to point out, is we're going to be using the equation Vs squared equals Vi squared plus 2AD. So Vf equals the square root of 11.61 plus 2 times negative 9.8 times 5.8. And that's going to give us a final value of 4.595 meters per second. Now there's a problem with our solution, and the answer is, if you take a look at our picture and we draw a horizontal line straight across, there are 2 points on this quadratic that the height above the ground is 5.8 meters. So the question is, how do we account for that? Well, if you take a look, we took the square root over here with Vf. And when you take the square root in mathematics normally, you have to deal with the plus or minus of that square root. Negative 3 squared is 9, and so is positive 3 squared, which means that we actually end up with two values for our final velocity as plus or minus 4.595 meters per second. So how do we know which one to use? Well, at the first point, it's obviously moving up, and at the second point, it's obviously moving down. We're looking for the distance to the second velocity, so we actually don't use the positive velocity, which means in this case our solution is negative 4.595 meters per second. And all we did is conceptualize the fact that because this is a symmetric quadratic, we were going to end up with two solutions. But now that we've done that, we can find the time of flight. The time is equal to V minus V naught over A. And remember, that comes from Vf equals Vi plus At, and we're just solving for t. Plugging in our values, you should end up with an answer of 1.654 seconds. So the total flight time to that point there, where the velocity is negative 4.595 meters per second, is 1.654 seconds. And why did we need that? Because now we can find dx using Vx equals dx over t. Why can we use t? Remember, it's a scalar quantity. So dx equals Vxt, which is equal to 13.83 times 1.654, which gives you a final distance of 23 meters. So step 1 was down here, step 2 was there, and step 3 was there. And I think by this point in the lessons, you've realized that that's a pretty standard procedure in dealing with these two-dimensional projectiles. Okay? So part 2 asks, what is the speed when he hits the building? Well, we've already dealt with this before. We have the final velocity in the y direction, and we know that the velocity in the x direction is consistent. There is no acceleration to change it. So if we draw our vector diagram, we know that Vx is equal to 13.83 meters per second, and we know that Vy is pointing down at 4.595 meters per second, which means our resultant velocity is this right here. And we'll call that Vt, and we know that it's at some angle below horizontal. So if we're going to solve this, first thing we do, realize it's a right angle triangle, perpendicular vectors are independent. Now we can use the Pythagorean theorem. Vt is equal to the square root of 13.83 squared plus 4.595 squared. And that's going to give us an answer of 15 meters per second. Notice again, I dropped the negative sign because I've associated the negative sign with my vector diagram. It's pointing down. I've called that negative, so we have the right direction here, but we need that angle. And to find that angle, we will again use the tangent of theta is equal to 4.595 divided by 13.83. Theta is equal to 10 to the minus 1 of those quantities, giving us a final theta value of 18.4 degrees. Therefore, our final velocity is 15 meters per second, 18.4 degrees below horizontal. So there we have it, my friends. Type 3s are done. Even when we're launching and hitting a different height other than the ground, or launching from a height on an angle, the philosophy is the same as long as you understand that you break down your velocity vector into components and deal with the vertical motion and the horizontal motion independently of each other. You have no problem getting to the solution. So practice these, and best of luck to you. Bye-bye.